In this presentation, I will begin by explaining what data types are and why they are fundamental in Java programming. Next, I will introduce the two main categories of data types, primitive types and reference types, highlighting how they differ in purpose and memory usage. I will then give a brief overview of primitive data types, which store simple values directly, such as numbers, characters, and Boolean values. After that, I will discuss reference data types, which store references to objects like strings, arrays, and user-defined classes. I will also explain why data types are important, including how they improve performance, memory management, and program reliability. Finally, I will conclude with a simple Java example to demonstrate how primitive and reference data types are used in real code. Data types define what kind of data a variable can store and how much memory is required to store that data. In Java, data types play a critical role in making programs safe, predictable, and efficient because the compiler knows exactly how each value should be handled. There are two main categories of data types in Java. Primitive types store simple raw values such as numbers, characters, and Boolean values. Reference types, on the other hand, store memory addresses that point to objects like arrays, classes, and strings. A simple way to understand data types is through a real-world analogy. Choosing a data type is like choosing the right container for storage, small or large, text or numbers, so the system knows how much space is needed and how the data should be used. In Java, data types are divided into two main categories, primitive types and reference types. Primitive types store raw values directly in memory. They have a fixed memory size, typically ranging from 1 to 8 bytes, which makes them very fast and memory efficient. Primitive types are commonly used for basic data such as numbers, characters, and Boolean values. Reference types, in contrast, do not store the actual value. Instead, they store a memory address, or reference, that points to the data stored elsewhere in memory. These types can grow dynamically in size and are used to represent more complex data structures. Examples include string, arrays like int array, user-defined classes such as student, collections like list, and other custom classes. This slide provides an overview of Java's primitive data types, which are fixed size types with clearly defined value ranges. Each primitive type occupies a specific amount of memory, allowing Java to manage data efficiently and predictably. For integer values, byte, short, int, and long differ mainly in memory size and numeric range. As the size increases from 1 byte to 8 bytes, the range of values that can be stored also increases significantly. For decimal numbers, float and double are used. A float uses 4 bytes and is suitable for less precise calculations, while a double uses 8 bytes and provides much higher precision. The char type stores a single Unicode character using 2 bytes, supporting international characters. Finally, Boolean represents logical values, true or false, and is commonly used for conditions and control flow. Together, these primitive types form the foundation of Java's data handling and performance. This slide introduces reference data types in Java. Unlike primitive types, reference types do not store the actual data value. Instead, they store a reference or memory address that points to where the data is stored in memory. One common example is string, which represents a sequence of characters, such as the word hello. Arrays are another reference type and are used to store collections of values, like a list of numbers. Classes and objects allow us to model real-world entities, such as creating a student object from a class blueprint. Finally, interfaces define behavior that classes can implement, focusing on what an object can do rather than how it is implemented.
Because reference types can grow dynamically and represent complex structures, they are essential for building flexible, object-oriented Java applications.
Data types are important because they tell Java how much memory to allocate for each variable and how that data should be used. By defining strict data rules, data types help prevent many common programming errors. They also improve performance and reliability because Java can optimize memory usage and operations when the data type is known in advance. In addition, data types allow the compiler to catch mistakes early, such as assigning text to a numeric variable before the program even runs. The examples on this slide show how different data types are used in practice. An int is used for whole numbers like age, a double for decimal values such as salary, a char for single characters, a boolean for true or false conditions, and a string for text. Together, these examples demonstrate how choosing the correct data type makes Java code clearer, safer, and more efficient. This slide shows the start of the cal method. When cal begins, Java creates a new stock frame for it. At this moment, the variables are declared but no values are used yet. Here, the variable a gets the value 10. Because a is an int, its value is stored directly in the stock frame of cal. Next, the variable b gets the value 20. Now both a and b are stored in the cal stock frame. This line calls the add method. When a method is called, Java creates a new stock frame for add on top of the stock. The values of a and b are copied into the add method. These are new variables, separate from the ones in cal. Inside add, a is increased by 1. This change affects only add's copy of a, not the original one in cal. Now, b is decreased by 1 inside add. Again, this change only happens in the add stack frame. Here, add calculates the result using its local values of a and b. The result is stored as a local variable in the add stack frame. The add method returns the value. This value is sent back to cal and stored in sum. After returning the value, the add stack frame is removed. This follows the last in, first out rule of the stack. Back in cal, a is still 10 and b is still 20. Only sum has changed because it received the returned value.